Yeah, I'm going to be talking about a collection of new results and then maybe mention a few tools that people will be interested in if they want to get involved with these sorts of calculations for computing broadly small mass ratio inspirals, which I mean sort of extreme mass ratio inspirals and intermediate systems. So as an overview, I'm going to focus mostly on EMRIs. I'll talk about the application to intermediate systems later on, especially once we've talked about the accurate waveforms from second-order self-force theory. So I'll overview just discuss EMRIs and EMRI modeling. And then I'll discuss the three key things we care about for gravitational wave modeling. That is, we need waveform templates that are very efficient to compute very rapidly for the data analysis problem, need to be extensive, cover the actual parameter space of orbits and inspirals that we have. And then finally, of course, they need to be phase accurate. And so I'll spend some time talking about that and extending on some of the, or presenting more results leading on from what Adam Pound talked about yesterday. At the end, I will also give just a brief advert for the Black Hole Perturbation Toolkit, which is a collection of tools, open source tools that you can use to actually perform these calculations, as I say, if you're interested in being involved in some way. The work I'm presented, I'm involved with in various ways, but of course, it's not just my own. There are a great list of collaborators that it's been a great pleasure to work with these guys and these people over the years. So I give them here and I'll list the relevant papers at the bottom of each slide. Okay, so to get started, first of all, what is it we're actually going to model, just to set some terms and why we're interested in modeling it. So the main motivation for what I've been doing is extreme mass ratio inspirals. These are binary systems where we have a small mass ratio. So we define the mass of the bigger body to be M1, the mass of the primary, M2 to be the mass of the secondary. Then I'm going to define epsilon to be a small number, i.e. M2 divided by M1. That's going to be small. Typically, the primary, I will consider, this is all just pure GR, I consider to be a massive black hole, and the secondary will be some compact object such as a stellar mass black hole or a neutron star. For LISA, we're talking about mass ratios in 10 to the minus 4 to 10 to the minus 7, otherwise I'll talk about later. These same techniques can be used to model systems more like 10 to the minus 1, once you include post-adiabatic corrections. What are the key features of these systems? Well, given the total mass, if this is a massive black hole, then these are millihertz gravitational wave sources, and therefore sources for space-based missions such as the LISA mission. Unlike ground-based sources tested so far, these will have hundreds of tens to hundreds of thousands of orbits deep in the strong field, which can last for many months or years in the LISA bands. These are extremely long-lasting signals in the strong field, very dynamical. They're very generic. There's no reason to expect spin alignment. So there will generally be spin on the primary and the secondary, and there's no reason to expect these to be aligned in any way for most formation mechanisms. And there's also likely, again, depends on the formation mechanism, to have considerable eccentricity. So eccentricities of binaries easily have no problem reaching 0.7, 0.8 when they enter the LISA band. And this leads to a very rich waveform phenomenology. The actual motion of the secondary around the primary would look something like this over a few orbits. It's a very rich structure, and as such, you get a very rich structure in the waveform as well. So this is the corresponding waveform, the plus and cross polarizations for this orbit here. As you can see, as a very rich, complicated structure. Unfortunately, though, they are very low instantaneous SNR in LISA, and that means we do need very accurate waveform templates in order to dig them out of the detector signal using match filtering techniques. So in terms of modeling, though we're actually going to model these systems, we're going to utilize the fact that we have a small mass ratio. As we know, solving the full nonlinear Einstein equations is hard. And so what we'll do instead is expand the metric of the binary about the analytically known metric of the primary. So write the full metric of the spacetime of the two bodies as the metric of the primary, typically the Schwarzschild or Kerr metric, plus maybe a first order correction and a second order correction. And as I'll argue in a moment, that's as far as we need to go for the physics we're interested in. We'll generally model the secondary as a point particle. So it will take this form. So all the mass is just at a single point. If you're considering spin on the secondary, you might also add a dipole approximation to this as well, but I won't be talking about it too much in this talk. And then the name of the game is to substitute this expansion into the Einstein field equations, expand order by order, and then solve those equations in powers of the mass ratio. Once you've done that, you'll be able to compute these metric perturbations. And from that, with an appropriate regularization scheme that Adam talked about more in his talk, that I won't really touch too much on, other than just to say that it's there, you can compute what's called a self-force, which is a force that drives the motion of the smaller body away from geodesic motion. And so that's that's the major goal, is to compute this self-force quantity in order to compute the inspiral motion of the secondary. As I said, you actually need to go to second order in the mass ratio in order to capture the physics you're interested in. And this is an important question when you do any perturbative expansion, like how far do I need to go to get the physics I care about? And the way we can understand that is by, it's actually done for a two timescale analysis, but by expanding the waveform phase as a leading order contribution, which scales as epsilon to the -1, plus a epsilon to the 0 contribution, and then there's a residual as well. And then the question is, how do these terms get contributions from different orders in the mass ratio expansion? So this leading order term is known as the adiabatic contribution to the waveform phase, and this is actually computed from the orbit average piece of that first order self-force I mentioned on the previous slide. And this conveniently can be related to fluxes through flux balance laws, meaning you actually avoid a calculation of the local metric perturbation at the location of the secondary, which kind of problematic divergences that need to be regularized. And so that's when if you use Tucholsky formulation or use Reggie-Wheeler in the past, or you know about these things, then that's how these things are typically easily calculated. And if you just have knowledge of that orbit average piece of the first order self-force or the first order metric perturbation, then that's generally good enough for detection and rough parameter estimation, or particularly bright EMRIs. But if you want to go beyond that and do the full science with extreme mass ratio inspirals, then you need the subdominant correction. So this first subdominant correction is called the post-adiabatic order, or post-1 adiabatic. In principle, they're a higher order, but this is the most you need to know. This contains the contributions to this are everything else in the first order metric perturbation, as well as an orbit average piece of the second order self-force of the second order metric perturbation. And you need this in order to extract all the sources that will be present in the LISA data stream. You might have heard EMRI's talked about the context of doing precision tests of general relativity, where in order to do those, you require this correction. And as we will see later on, it has a potential application to intermediate mass ratio inspirals. The reason for this is you can see is that once I've got these two corrections, once these two leading terms in the expansion of the phase, the residual scales with the small mass ratio. So if you have a mass ratio of 10 to the -4, this could be potentially very small, depending, of course, on an unknown coefficient here. And as we will argue, and as we'll see later, the coefficient here is actually quite small. And so as long as your mass ratio is reasonably small, this will be a very good approximation to the phase. So even a mass ratio of 1 to 10, you might find you have a very small residual error in your waveform phase. So the name of the game is to compute these two things, at least in terms of the accuracy of the waveform. Just say a little bit more about waveforms. They're going to come up throughout the talk. So what we will do as a standard is we'll split the waveform into an amplitude and phase. So here's the total waveform, which we'll write in its complex form as the plus polarization plus I times the cross polarization, which we'll write that as an amplitude times a phase factor. Generally, we will decompose the waveforms into a harmonic basis. You have a spherical, or in this case, spheroidal harmonics. This S is the spin rate -2 spheroidal harmonic basis that you might have seen if you solved the Tucholsky equation, for instance. There's some amplitudes, and here is the phasing. I'll actually absorb this A and this S into a single term, this capital H here, for later convenience. And then the waveform phase is given by integrating over the orbital frequencies, which are now, for geodesic, those are fixed. They specify the geodesic, but now they're slowly evolving due to the back reaction of the metric perturbation on the small body. So the waveform phases can be broken up into these three terms relating to the azimuthal, radial, and polar motion, and each one of those is an integral over the time evolving frequency. How do those look in ways you might be more familiar with? So just to give an example of how EMRIs are different. So with ground-based detectors, the LIGO-Virgo setup, the longest observed signal so far is less than a minute, and that's the binary neutron star GW170817. And you can see this beautiful in the frequency time plot. You see this chirping signal here. For EMRIs, you have a great many harmonics, and each one of them looks somewhat like a chirping signal. They're not exactly the same. I'll highlight some key differences in a little bit. But if you actually look at the time frequency diagram for an EMRI, here, of course, just a simulation, you see what you have is basically a system of chirping, what we call voices, or often called voices, are these the harmonics of the waveform. And so each one of these looks individually kind of like a chirping binary, but there are many hundreds or even thousands of them that you might be able to detect for each individual source. So it just kind of shows you the additional complexity you might get with EMRIs. Okay, so having defined a few terms.
Sorry, just to interrupt. So a quick question probably is that, do we know why exactly you have this set of chirping signal instead of one if you have EMR? I mean,
yeah, of course. It's because your system isn't quasi-circular. Your system is highly processing and it's also highly eccentric.
Oh, I see.
So
I see. But if it is
these signals all correspond to different harmonics of the radial, particularly the radial motion, and the inclined motion, the polar motion, which can give us precession. You would see exactly the same thing if you had an eccentric source in a ground-based detector. It's just that we tend not to have eccentric sources because we just see them at the end, and they tend to circularize by that point.
So for intermediate mass ratio inspiral also, for eccentric orbit, you will have this set of, like, instead of one, you have set of chirping signal.
You will. Again, it depends how much of the signal you see. If you're just seeing it right at the end, and depends on the formation mechanism, and that's much less well understood for intermediate mass ratio systems, I would say. But in principle, yes. There's a lot of work going on in ground-based sources, adding eccentricity to waveform models at the moment. They tend to focus on very small eccentricities, just small perturbations away from circular. But for EMRIs, this is, I forget actually, what it says here, so this is 0.7 eccentricity, so it's a pretty highly eccentric system. It's very eccentric.
I see.
Great, no problem. Okay, yeah, so having just defined a few terms and talked about how EMRIs may be a little bit different to sources you have from ground-based observations so far, what are the key goals and what are we trying to achieve? Okay, so with all types of sources, of course, we care about these three things. We want them to be accurate, we want them to be efficient to produce, and extensive. And what does that mean in the EMRI context? So for accuracy, we want the phase error to be very low, much less than 1 radian over the duration of the inspiral. And it's a very long inspiral, lasting years and many hundreds of thousands of cycles. And we need to do a coherent match filter across that. So we need an error less than 1 radian, so the two signals do not go out of phase. So the template and the true signal do not get out of phase. And from my previous thing that I mentioned, that means you need both these adiabatic and post-adiabatic corrections to modeling. Efficiency, we need to produce each one of those year-long signals or multi-year-long signals in definitely much less than a second, because we've got to produce millions of these templates in order to perform the data analysis task. True in all gravitational wave searches, and here no less. So we need to do very rapidly, very long signals containing all this phase information on order of a few milliseconds, really. And finally, of course, it must be extensive. As I just said, most ground-based sources for ground-based detectors are quasi-circular, so they have a smaller parameter space. EMRIs, though, are fully generic. There is no reason to expect the spins to be aligned, so they'd be arbitrarily processing, and they are often, depends on the formation mechanism, but the main mechanism will probably give you very eccentric EMRIs when they enter the LISA band, something around 0.7, 0.8 eccentricity. So models must also span this parameter space. So for the rest of my talk, I just want to talk a little bit about what the progress is in each of these, focusing primarily on the accuracy one, because some really interesting new results there, but I'll give you, to begin with, some overview of where we are in terms of efficiency and extensive coverage of the parameter space. So in terms of efficiency, the main challenge is the waveform is very long, and there are a great number of harmonics that you have to sum over. So here is a slightly simplified model. We're just looking at inspirals into a spatial black hole. So we have less harmonics. We have an azimuthal harmonic and a radial harmonic related to the radial libration and the time it takes to go around the azimuthal one. And we're decomposing into spherical harmonics here. So this is what a waveform would look like. And typically you have something of the order of 3,000 modes that need to be included at each point in time in order to compute this waveform. And then you've got a time series that must last many years at the sample rate of the least emission, which I think is once every few seconds or so, at least. So there's a lot you have to compute. So we've done some recent work on this, where we've actually interpolated these amplitudes across the parameter space using a combination of what's called reduced order modeling and a neural network interpolation, because these amplitudes don't need to be known super accurately. And so neural networks are quite good at that. But the phasing does need to be known very accurately. And we're able to show in this work, it's given in this letter at the bottom from a couple of years ago now almost, that we can compute a waveform. This is an eccentric waveform, again, about 0.7 eccentricity. This slow, which is the blue curve, you can barely see it, is the very accurate one that's computed very slowly. And this new model, which is very fast, is the yellow curve, which, as you can see, beautifully reproduces it. The phasing in this model is just adiabatic, though. We don't use the post-adiabatic corrections, but it is in principle easy to extend once those corrections are known. As I'll highlight later, they're not at the moment. It's also, we interpolate over time as well. So we compute the results at a bunch of points in time, and then we spline interpolate across that. And so a combination of the spline interpolation and the neural network interpolation for the amplitudes is actually, these are linear algebra operations, and these are extremely efficient on graphic processor hardware. And actually means that with this particular setup and arrangement, we're able to compute fully relativistic, up to first order mass ratio, waveforms in much less than 1 second. So we compute a year-long worth of data, a year-long signal in significantly less than a second, with a mismatch with the true slowly computed accurate thing of less than 10 to the minus 4. And so that's the first time we've had kind of, I say fully relativistic, which is a first order mass ratio in this expansion, fully relativistic waveforms. So they're making no weak field approximations and no kind of kludging of the waveform sort of approximations. These waveforms have already been used now in the next LISA data analysis, data challenges, as well as computing figures of merits. And they are actually, all this software is publicly available. It's available to you on the black hole perturbation toolkit. And you can use it to compute EMRI waveforms very quickly. I'll discuss this again towards the end. Just to highlight that, this new model, this fast EMRI waveform, this FEW model, is already being used in data analysis studies. There's one here that we carried out last year, led by Michael Katz. And here we can inject a signal as an example, and we can actually perform MCMC parameter estimation. And because we have a GPU implementation, it actually only takes a few hours rather than maybe a few days as it might take with CPU implementations. And as an example, we injected a few waveform when we recovered it, but we can also attempt to recover it with these kind of kludge models that have existed in the past, where people make weak field approximations, or they make just use the quadrupole formula to compute the waveform. And you can see that when you do that, you end up with significant biases in the various parameters of the waveform. And so it shows that the value of using obviously the fully relativistic results. So just to highlight that, we can now actually compute waveforms that contain all of the kind of self-force information that we have on a very rapid timescale that's good enough for data analysis. And this has actually been used practically now. So we're hopeful that model will become the future kind of workhorse for EMRI modeling. In terms of extensive models, like actually covering the parameter space, first thing to do is to define how big that space is. So going back to now to a fully generic waveform about a rotating black hole. So now we have radial and polar librations. We have waveform structure that looks like this, where now we're summing over L, Mn, and K indices. So the Mn and K correspond to, the azimuthal, radial, and polar harmonics. There are a bunch of parameters that define the symbol. Some of these are extrinsic, so these are easy to deal with because they just change how the gravitational wave projects onto the detector, so position on the sky, orientation, and the azimuthal phase at initial time. More challenging for the modeling side is the intrinsic parameters, and these fundamentally change the gravitational waves in some way. Some of these are easy to deal with. The distance to the source just scales the whole amplitude of the signal, and likewise the mass is of the two bodies. They just set the total mass and the mass ratio, and with our mass ratio expansion, they just scale out. But then in terms of modeling, actually covering the spin of the primary, as well as particularly the constants of motion that set the initial energy, angular momentum, and Carter constant, or the semilateral vector eccentricity and inclination, for instance, those are very challenging to cover from a modeling perspective and actually fill out that space. Likewise, the radial and polar phase initial time. And so there's been a lot of work kind of slowly filling out the space. And until recently, people have computed some of these fluxes or these self-forces at individual points in this space, but never actually tiled the space and computed full inspirals. That changed last year. For the first time, we actually put together everything required to compute a fully relativistic, again, just up to linear in the mass ratio, generic, adiabatic, so just using fluxes, EMRI waveform. So for this, we tiled the parameter space for a particular spin, and I have 0.07 m. So this is the spin on the massive black hole. By running a generic orbit Tucholsky code to compute the rate of change of the energy, angular momentum, and Carter constant, as well as the amplitudes A for the waveform. Here then is an example of actually evolving the trajectory through the phase space. So this is the eccentricity. P is the semilattice rectum, which is a measure of the distance of separation of the two bodies. And this X here is a measure of the inclination. It's cosine of the theta inclination angle. And you can see it evolving through the 3D space until it reaches this plane, which is the separatrix, which divides bound and plunging orbits. And then these other curves are just the projections onto the different planes. As you can see, we have a year-long waveform. This isn't computed rapidly, I must say. This is a very slow calculation. It's not yet put into that new fast EMRI waveforms framework, but it has a considerable eccentricity of 0.25. It's reasonably inclined. And you see the waveform is very rich in structure. These are with two different initial, the blue and red here are two different initial starting conditions. But you can see it's a very complicated waveform based because of the azimuthal and the radial and polar librations. This is the beginning end of the waveform. So this is the beginning, this is the end. So that's the first time it's done. It's far too slow for data analysis at the moment, but at least everything is put together. And the goal is going to be to put that into that fast framework I mentioned earlier. In terms of covering the parameter space, another way you can think of it as well is also what representation do I want the waveform in? As many of you will know, a lot of data analysis is performed in the frequency domain, certainly for ground-based signals. Now for LISA, that's not so clear it's going to be the best way because the detector is moving itself, the constellation of satellites, and so it's not clear a frequency domain or time domain, or maybe time frequency might be the best way to do the analysis. It's still an open question, but you certainly might be interested in frequency domain waveforms, depending on the analysis. So far we've been constructing waveforms in the time domain, but in that same work where we did this generic inspire, we also showed how you can directly compute waveforms in the frequency domain. So again, just to quickly go over that, here we have an example of our waveform. We have some amplitude and some phase. Again, this H is a combination of these two quantities. And then we can take a Fourier transform of just a particular voice, so just one of these modes of this sum. This is just a definition of a Fourier transform, just writing it out here. And then almost all of the terms here there'll be no contribution to this rapidly oscillating phase, except when these two terms are roughly equal. And so we can make use of that as long as this amplitude is slowly evolving, which it is for EMRIs, because the small mass ratio, to perform what's called the stationary phase approximation. So we can expand this phase out as a Taylor series around what's called the stationary time in this way. And we can then approximate this Fourier integral, so this Fourier transform in the following way, in what is a pretty standard way, like this. So great, that's one way we can then just take the information we have and compute, instead of summing up to build the time domain waveform from all these amplitudes and phases, we can then, with the same amplitudes and phases, compute the Fourier domain waveform. But there is a particular problem with this. As I said at the beginning, an EMRI does look like a lot of chirping binaries, but that's not, if you look carefully, they're not all chirping each one of those signals. Some of them have a different behavior. As an example, if you look at the L equals 2m equals 2 mode, this is an eccentric orbit, just at no polar librations, it's not precessing, and a radial harmonic of n equals 20, so the 20th overtone. Then if you look at the amplitude of that mode, it's actually decreasing in time. This is a log scale, so it's crossing over. This is complex as well. And the frequency, it increases, it sort of chirps, but then at some point in time, it starts to decrease as well. So it doesn't have exactly the same chirping behavior. This actually causes a problem, particularly this turnover in the frequency causes a problem for the stationary phase approximation, because as you saw in the formula before, you have a derivative with respect to the frequency in the denominator of that equation. And so that means if you just try and apply the regular stationary phase approximation to these waveforms, which has been done in many gravitational wave contexts, it actually diverges at this point in the strong field. And that can be overcome. And actually just the way you do it is just by extending the stationary phase approximation to higher order. And so it's something we do in this work. We extend it to the next order. We get a new, more complicated version of the stationary phase approximation. And that then we apply to the signal and show that it agrees with a discrete Fourier transform of the time domain signal. I see a question there. If you want to go ahead and ask at this point, Zach.
Yeah, Niels, Shayok speaking.
Yep.
So you said that the charting pattern could be different. Why does it happen?
So yes, that's an excellent question. I don't think I have a slide on this. It basically happens because the radial frequency goes to 0 at the separatrix. So this has 20 times the radial frequency as part of the mode frequency. So it's m, so it's 2 times the azimuthal frequency plus 20 times the azimuthal frequency, the radial frequency. As you progress into the strong field, as you approach plunging, that tends to 0, that radial frequency, and so the frequency starts to drop. This is not, it's just a generic feature of eccentric binaries. And again, when ground-based sources start to look at this more carefully, they will find the same thing as well.
So this is only because of the eccentricity. If I had taken a circular and inclined orbit, this should have not been the case. Oh no, there also you could have gotten this because of two frequencies are actually competing with each other.
Exactly. Yes. Yep. So it would be possible there. It's not quite for the same reason, but it would be possible because you might get the frequency dropping depending on how the two frequencies compete.
Yeah. Thanks.
Great. Okay, so that was just a quick overview, kind of the status of where we are in terms of efficient waveforms. So we do have models now that don't use PN approximations, don't use quadrupole formula waveforms that are very, very rapid and can be used for data analysis and are practically used in data analysis now. And we can also start to cover the full parameter space minus the spin on the secondary at the moment, although there's a lot of calculations being made in that recently. What I'd like to focus on for the remainder of the talk is really discussions about accurate waveforms. This really follows on, as I said, from the talk given by Adam Pound yesterday. And so for that, it's really about using second order self-force and computing these post-adiabatic waveforms. Again, I won't give many details of this. It's a pretty long calculation that's been going on now for best part of a decade, actually, with recent results coming out just in the last couple of years. Just to remind you, as I said, the goal is to expand the metric perturbation. Expand the metric of the binary about the metric of the primary. So this would be a Schwarzschild Kerr metric, this G bar plus first and second order corrections. I'm not going to give the details, but just to say that we actually practically do this, as Adam would have talked about yesterday, is by doing a 2 timescale expansion. So we have these slowly evolving amplitudes. These evolve with the orbital frequency and a rapidly evolving phase. This is actually what we substitute into this expansion here rather than this. We'll of course then do a tensor harmonic decomposition, making use of the fact that we have a spherical background. We're going to work in the Schwarzschild spacetime, so this G bar is Schwarzschild. And then practically we have to pick a gauge to work in. So we work in the Lorentz gauge, which is convenient that it helps work for this regularization that has to be done to compute the self force. Adam would have talked about this yesterday in terms of the matched expansions required to go through all of that. And so what we end up with is a system of ordinary differential equations, where these E0 is the linearized Einstein operator in the frequency domain in the Lorentz gauge. And then on the right-hand side, we have some sources. At first order, this is just a compact source. If you like, it can be just defined on the world line, but this is actually a non-compact source. It's non-zero everywhere in the space-time because this term here is the second order Ricci. It's formed of quadratic combinations of the first order metric perturbation. Don't worry if that don't worry if that isn't clear. If you're interested in details or how this goes, there's a really nice paper laying this all out by Miller and Pound out last year. What I want to talk about more so is results and what we've been able to do with this framework very recently. And from here onwards, although I've talked about more generic systems, hereafter I will just talk about quasi-circular binaries with, if there is spin, they'll be aligned or anti-aligned with the orbital angular momentum. Okay, so the first thing I will talk about is the calculation of the gravitational wave flux from these systems. I'll just define a few terms. Just as I said before, we'll decompose into spherical harmonics at this point, no longer spheroidal harmonics. We'll consider the primary to be non-spinning. And we'll do it this way. So we have some amplitude, and these are the spin weight minus 2 harmonics, spherical harmonics. We will split this time in amplitude and phase, where both the A and the phi are real functions. Before perhaps wasn't clear, but A was actually a complex function. just the way it's done in perturbation theory. And then we'll define the flux and the frequency in the standard way, where the flux is given by 1/16 pi times the time derivative of the amplitude, absolute value squared. And we'll define this frequency to become from the 2-2 mode of the waveform. So we take the phase of the 2-2 mode, take its time derivative and divide by 2, and we'll call that the frequency. We'll then, in order to present results, define what an inverse separation parameter, x bar. If you're used to post-Newtonian calculations, it's very similar there. That's written in terms of m. This capital M here is the total mass of the binary times the frequency raised to 2/3 power. And the weak field, this frequency is equal to the orbital frequency. But there's a slight difference, basically, in a PN sense from tails when you're in the stronger field. And so this x bar is also equal to the usual PN(x), again, if you're familiar with that. In order to talk about results for the fluxes, and it's actually pretty convenient to, first of all, normalize the flux by the Newtonian term. So the leading, for the 2-2 mode, for the quadrupole term, for instance, so take the flux divided by the Newtonian term, and that gives us our f hat. So now we have f, this the Newtonian term is the well-known 32/5 x to the 5 nu squared, where this nu is the symmetric mass ratio. And this means that in the limits, as x goes to 0, which is you move into the weak field, f hat always tends to 1, as in it tends to the Newtonian result, or the leading post-Newtonian result. And when we write our fluxes, before we expand everything in the mass ratio, the small mass ratio here, we're going to, as Adam talked about in his talk, expand everything, re-expand. So it's not a resummation, it's just a re-expansion of everything in terms of the symmetric mass ratio. We do this because we understand that, like, the full system, that's the symmetries it should have. There should be no difference if I change the M1 and M2. Shouldn't change the physics. And so it's kind of reimposing that result onto the calculation. So just re-expand everything in terms of the symmetric mass ratio. So I have a first order correction from the first order metric perturbation, as well as a second order correction, which enters at nu cubed. Okay, so what we did is we went ahead and made our second order self-force calculations. Again, I brushed over the details, but having done that, what we've been really interested in doing recently is comparing those with numerical relativity calculations. So let me just talk you through how that's gone. So here what I'm plotting is that normalized flux. So this is divided by the Newtonian term, so 1 is up here. That's where you expect things to tend in the weak field. And then it's a function of that inverse separation. So this is weak field results over here, this is strong field, and in the test particle limit, this is the location of the innermost stable circular orbit. That's the frequency of it. In blue, I'm plotting the results from a numerical relativity simulation. So taking that simulation, applying those calculations I showed in the previous slide to compute the flux. It's from this particular simulation from the SXX catalog. And this is the blue curve here showing the flux. At the top, I'm counting backwards from the peak of the numerical relativity waveform. So this is 2 cycles before the peak, 4 cycles, 10 cycles, and 40 cycles before the peak of the waveform. So that's what we get from numerical relativity, which of course gives us modulo numerical round off the true answer. For this case, a mass ratio of 1 to 10. So Q here is 1 over epsilon. It's the large mass ratio. We can plot on as well the post-Newtonian results. The highest known result for the 2-2 mode, that's what this is for, is the 3.5 PN. You can see it almost agrees with the numerical relativity as you can move to the weaker field. You can also plot the first order result. So this is what you get from just the fluxes you would get from a standard first order Reggie-Wheeler or Tucholsky calculation. It's been known for decades now, and you can see it doesn't agree very well with numerical relativity. But then once you add on the second order corrections, suddenly you get this really nice agreement between second order self-force and numerical relativity. As you can see, the agreement is actually very good even in the weak field. You can see it's agreeing quite well with post-Newtonian theory, which contains all orders in the mass ratio up to that order in the post-Newtonian expansion, and then agrees beautifully with the numerical relativity result. Basically, within there's some noise here, there's some residual oscillation, which can be for a variety of reasons, residual eccentricity and motion of the center of mass of the binary. But we're basically within the error bar until towards the end, where actually our result breaks down as you approach the innermost stable circular orbit with the current implementation, because our 2 timescale expansion breaks down there at the moment. We're in the process of extending that, but at the moment, that's why this tick appears down. So So that's really nice to see. It was really unexpected. Perturbation, this is a perturbation theory result being applied to a mass ratio of 10:1, and we see nice agreement once you extend it to second order in the mass ratio. So showing that perturbation theory can probably model much more than just extreme mass ratio inspirals. It probably can cover a large portion of the intermediate regime as well. We can actually totally abuse perturbation theory and just say, well, why don't we just let the mass ratio equal 1? So we have 2 equal mass binaries now at this point. Again, all the coloring is the same. The blue is the numerical relativity result. The first result is miles away. You wouldn't expect it to agree. But amazingly, the second result doesn't perfectly agree with numerical relativity. You don't expect it to here. This is perturbation theory applied to a comparable mass binary. It still agrees really nicely with PN and numerical relativity for a large part of the parameter space. And of course, our result does break down strongly as you approach the unstable circular work. So there, even a Q equals 1. Again, not saying you would use Q equals 1. You wouldn't model Q equals 1 binaries using this, but it is interesting to note how well it works even in this really this domain far away from where you think it would work. There's a question, Sayak, if you want to go ahead.
Yeah, actually, if I remember the previous slides, so the expansion actually is in the mass ratio, right? So no, you don't have to go to the slides. I'm just asking the question.
Okay.
So, but when the mass ratio is equal to 1, then I should expect that the higher order terms should contribute, right? Am I misunderstanding?
So I'm doing an expansion in the symmetric mass ratio. So when the when you have equal binary, it's a quarter. So that's part of the way it helps. So the terms in that sense, at least, are getting smaller, but you don't know what the coefficients are, but it does seem to work out that it works very well in the comparable mass case.
So whenever the expansion,
in some sense, if you like, you can think of a quarter as being a small number.
Oh yeah, that I understand. Now I'm asking, so in the expansions, when it is done, it is not done in terms of mass ratio at all. It is always done for symmetric mass ratio.
The whole calculation is carried out with a small mass ratio. So M2 divided by M1. And only at the end do we re-expand onto the symmetric mass ratio. But there's nothing funny going on there. It's not a resummation. It's just a re-expansion of the, so you're still just truncating at the same order. You're not getting or losing any information by doing that.
Okay, got it. Thanks.
No problem. Okay, so that was just the 2-2 mode, but we can compute more modes. And we can actually, as an example, let's look at the next subdominant mode, the 3-3 mode. So here's the same results again. Actually, now the second order result doesn't agree so well with numerical relativity. There was a bit of a gap. And in fact, the first order result is so bad, it's not even on the scale of this plot. So it's certainly doing better than first order, but there is a small difference for sure. How can we perhaps understand that? Well, if you look at the post-Newtonian series for the 3-3 mode of the flux, then you can see that the third order flux, the third order self-force result, appears in the first subdominant term of the PN series. So actually, apology, there's an x to the 6th missing from this leading term here. But in this first subdominant term is where you get, so we capture everything up to nu cubed through our calculation. So we get all of this term and this, but we do not capture this. If you compare this with the 2-2 mode, then you can see that the first time the nu to the 4th term, which is a third order self-force term, appears, is in the 4th term in the PN series. So there's already some suggestion there that you would expect our results to be better for 2-2 than for 3-3. Of course, it's a bit disappointing, perhaps those things don't agree so well, but it turns out that you can actually do a very simple resummation to include some information from the post-Newtonian series, or possibly reinforcing some symmetries in the system. What you can do is you can take our self-force results, our first order plus second order result, divide by the leading post-Newtonian term, re-expand this up to order nu q, up to nu squared, and multiply by the leading term again. This resummation has the property of ensuring that in the weak field, our results agree with the post-Newtonian series. That was the motivation for trying this. And lo and behold, when you try this slightly resummed series by including just information from the very leading post-Newtonian term, suddenly then your second order results, or our second order results, agree again very nicely with the numerical relativity simulations. So you can certainly make them agree much better. Something that Adam didn't talk about yesterday is that we can also include spinning binaries. Although our calculation is based around a perturbation of a Schwarzschild black hole, so long as the spin on that black hole is small, the big black hole, we can include in the calculation, and we can also include arbitrary spin on the secondary as well. Both of those things contribute to post-adiabatic order. So to facilitate those comparisons, we define a few extra symbols. These are just basically ways of mapping between the small mass ratio and the symmetric mass ratio. Just the same as we did Q to nu, when you're mapping spins as a little bit extra. Now we can compute this linear in spin calculation, this F1, the flux due to the spin on the primary, directly from our second order calculation, and we have. But it happens to also be equal to the linear in A1 Tokolsky flux. So if you compute a Tokolsky flux and just linearize it in the spin of the primary, it's the same result. Likewise, we can add on the spin of the secondary. That's been computed by a lot of people recently. We did it ourselves in this paper here, but there's also some other recent papers that have done it in the last year or so. When you do that, you can actually also model, capture the flux result for spinning binaries. So here's an example where we have a spinning secondary. So now a mass ratio of roughly 1 to 6, which corresponds to this symmetric mass ratio. The primary has a very low spin on it, and the secondary has a spin of -0.8. Here again, I'm showing the blue curve as numerical relativity. The PN is this dash curve. I'm not showing the first order result, but just the second order result. If you don't include the spinning correction, then it doesn't agree very well. That's this green curve. But once you include that spin correction from the spinning fluxes from those papers I just mentioned, you can see it jumps up beautifully and agrees again with the numerical relativity result. That's with a spinning secondary, but no spin on the primary. We can also do the situation where we have spin on the primary. In this case, a low spin, 0.1. In this case, we also have spin on the secondary, also 0.1. And again, we can see that's the second order result, which is quite poor when you don't include those spin corrections, but when you include them, it agrees again beautifully with this numerical relativity simulation, at least until you get towards the innermost stable circular orbit. This is for a mass ratio, I should say, of Q of 8. So, well beyond where you think perturbation theory might work normally. And finally, a key question, something else we looked at is how does our results scale? How does the residual from our results scale when compared to numerical relativity? So we believe that we've calculated everything through order nu cubed in the mass ratio, and we can get some evidence that we've done that by comparing to numerical relativity. So what we do is we take the fluxes that we've computed and numerical relativity. We first of all subtract, so that's the orange circles and the blue squares, the numerical relativity and cell force. We then subtract off the first order cell force result, and we should get something that has a residual that scales as nu cubed. That should follow the line of the second order result. That's what we get. And then when we once again subtract off the second order result we've now recently computed, we should get a residual that scales as nu to the fourth. Now this is very clear and seems to be working very well for the 3-3 mode, but it is not so clear. There's quite a lot of noise in the numerical relativity simulations. That means it's not quite clear. There's some evidence that it's working, but it's not perfect for sure. But it looks like the residual scales approximately as you would expect. This is because those small oscillations that are still present in numerical relativity simulations, and also because by subtracting off the first 2 cell force corrections, you're going down almost 3 orders of magnitude, and you're just approaching the noise error or the error in the numerical relativity simulations. So it looks like we do, from this, we think we capture all of the results up to nu cubed. Okay, so to conclude, I just want to talk about waveforms. So again, Adam showed a couple of these, but I'll just give a few more examples here in my talk. How are we going to do that? We haven't actually computed the second order cell force, which should be used to drive the inspiral at this point. It's still an ongoing calculation, but we can use a sort of flux balance law. So we can say that the flux of gravitational waves must be equal to minus the rate of change with respect to, this is retarded time of the bonding mass, and the bonding mass is equal to the binding energy plus the masses of the 2 bodies. We can expand this out like this. So with the derivative of the binding energy with respect to the orbital frequency, as well as the binding energy also depends on the mass of the primary and the spin of the primary. Now, these terms formally contribute to this calculation, but it turns out that the mass evolution and the spin evolution of the primary is very small. So they enter at this order, but the coefficient is extremely tiny because they're proportional to the horizon fluxes. which if you've calculated this one, you know is very small. So at the moment, we don't include these in our calculation. We set all of these terms to 0. That's not completely consistent, but we have checked that it basically doesn't make any difference. Future work, we will add them in. But using what's left, this relation, we can get a equation for the rate of change of the orbital frequency, which is that flux divided by the rate of change of the binding energy with respect to the orbital frequency. Once we have the orbital frequency, we can integrate that one more time to get the phase of the waveform. So the flux is what I've presented here, and that we gave that in this recent letter. And this binding energy, I didn't talk about it, but Adam would have mentioned it yesterday, but that's in another previous letter we had out in 2020, where we computed that as well. And using the combination of these two, we can compute the evolution of the binary. Again, I just want to remind at this point about how the scaling of the phase, before we look at the results, about why this perhaps works so well, is that once you have these first two leading terms, one goes as order nu to -1 and then order nu to the 0, the residual scales as order nu. So, if you have a mass ratio of 10 to 1, then nu is about 0.1. And so you expect a small, depends again on an unknown coefficient here, but it turns out that's not too big. Another key feature is if we actually expand the phase like this, we can either solve these equations as a differential equation, or we can further expand this in powers of the mass ratio. But if we do that, then we can actually interpolate these two things as functions of frequency, as well as the amplitude of the waveform. And we can actually construct waveforms for any mass ratio in milliseconds. So it's already built in to be extremely fast to calculate these waveforms. So these waveforms are, this can then be absorbed into that fast every waveform framework I talked about at the beginning. Okay, in terms of waveforms then, here is an example. Again, this is Q10, so mass ratio 1 to 10. This is the numerical relativity data from this particular simulation from the SSX catalog. If I compare this to a first order result, once I switch Q to nu and do that re-expansion, it does okay at the beginning, actually. It's not so bad, but it quickly dephases with the numerical relativity results as perhaps would be expected from what you've seen so far. But once you include the second order calculation, we now find that actually we agree beautifully with the numerical relativity result up until close to the merger, where, as I said, our current 2 timescale approximation breaks down. So you get this really nice agreement with this numerical relativity simulation at EM mass ratio of Q 1 to 10. Just to zoom in on the end there, just so you can actually see the dephasing. This blue curve again is the first order result, the adiabatic inspiral. That's dephased long ago, but the second order result, this post-adiabatic inspiral, has only starting to dephase here when you're just 1, 2, 3, 4 cycles from the peak. So that's just 2 orbits away from the peak of the waveform. So it really does very well, it seems, for these near comparable mass binaries. And we can look at that separately as an amplitude and phase. Here is the amplitude. So again, black is numerical relativity. Blue is the adiabatic result, and the post-adiabatic result you can see agrees really nicely. There's a slight difference appearing towards the end, but that is expected. Likewise with the phasing, this is the phase difference between numerical relativity and our 1 PA waveform. You can see it's remains small and only grows towards the end, but even then it's only up to 0.05 of a radian or something as you're approaching the end of the waveform. So it really does very well. We can, of course, really abuse perturbation theory as we did before. Here is an example at Q equals 3, so mass ratio of 1 to 3, where you really do not expect perturbation theory to work well at all. And you can see it does track the phase of the numerical relativity waveform remarkably well. Now, of course, towards the end, it does dephase, of course, and you can see that on the inset here, that the blue and the yellow curves are dephasing, but that's expected. And I do want to really emphasize this. We're not saying you should use perturbation theory to model Q equals 3 binaries, but we are saying that at Q equals 10, it does remarkably well, and we know how the error scales in these waveforms. And so Q equals 20 and 30, you really can be using perturbation theory, and probably at Q equals 10 as well. It looks like it's very promising. Again, this is just to show how well it does work at Q equals 3, but it's not perfect. It is, of course, dephasing. Okay, so yeah, okay, so that's what I want to say about waveforms. If you want more details, there's a letter that's currently on the archive under review at the moment. giving some more examples of that. Okay, so just to conclude, just a little bit of an advert, really, just to say, if you're interested in this sort of stuff, this is a good way you could get involved, or a way to make the calculations easier. So these black hole perturbation theory calculations and these self-force calculations are now becoming pretty involved. They're much bigger in scale. And if everyone had to just write their own Tucholsky integrator from scratch, or their own code to compute a metric perturbation from scratch, we just wouldn't make a lot of progress. And so recently we the last few years, introduced this project called the Black Hole Perturbation Toolkit, which is a collection of open source software. You can find it at this address, bhptoolkit.org, which will give you code that will compute things like solutions to the Tucholsky equation. It will compute fluxes, mostly for circular orbits. It will compute Reggie-Wheeler perturbations. It will compute Lorentz gauge perturbations. It will compute quasi-normal modes, anything related to black hole perturbation theory. And it's a pretty active project. It's already in the few years that it's been around. There's at least 78 papers that we know of that have actually used it in some part of their calculation. And because it's open source, it's free. You're welcome to use it. You're welcome to ask questions about it. And so if you are interested in this sort of work and would like to get involved, this is a great place to find resources, I would say. In terms of learning about it, there's an entire workshop we did in 2020 virtually due to the pandemic, but that actually worked out quite well because it's all recorded, it's available on YouTube. If you just search BHP Toolkit, I'll give you some overview. And you can also follow on Twitter for updates about what's going on there. So if you are interested in this stuff, this is a great place to find useful resources. Okay, so just to conclude then, in terms of future directions, I talked about these adiabatic waveform models we have. Currently, those are only, and they're very fast. They are good enough for data analysis, but they're only for Schwarzschild inspirals. Eccentric, yes, but they don't have spinning primary or spinning secondary. And so, future directions are extend those models into those directions. There's second order self-force calculations, and these post-adiabatic waveforms that agree so well with numerical relativity. Something I'm really excited about, but they are only for quasi-circular inspirals into a slowly rotating black hole. And so there's a lot of work to be done there to extend those to eccentric inspirals and into inspirals into rotating black holes and add precession and all that. As you saw, those waveforms, you saw particularly in the flux plots I showed you, they break down the flux. The disagreement is very strong near the innermost stable circular orbit. And there's actually ongoing effort now to overcome that by attaching a transition to plunge and ring down to compute a full inspiral merger ring down waveform from this self-force approach. We hope to have that done this year at least. And yeah, just to maybe emphasize this point, I've talked about modeling EMRIs almost exclusively, but the last results in terms of comparison numerical relativity show that you can probably use this to model intermediate systems, which means it has applicability to ground-based detectors as well. So mass ratios of 1 to 10, 1 to 20, that sort of range, which the LIGO, Virgo, and in future Kagra detectors are going to see, you can probably model some of those using black hole perturbation theory. So great, I'll finish there. Thank you very much.